Good morning. There's post-quantum crypto. I'll talk a bit about quantum computing and post-quantum crypto. I'll try to make it not too scary because as you know, crypto talks, they tend to be a bit intimidating. Maybe one reason is that speakers don't always, simplify their stuff, or they don't express it in a very intelligible way. But there is some basic prerequisites, the stuff that you need to know. So you must all be familiar with these equations. It's very basic stuff, Schrödinger equations. If you have a PhD in physics, it shouldn't be any problem. Of course, I'm kidding. You won't see any of these. I'll try to explain what a quantum computer does. How about without too much detail? I will focus more on the implications in terms of security and crypto and how you can fix it. So first of all, some quick background on quantum computing, because if you read the news and social media, there's a lot of bullshit and people telling you, oh, there will be a quantum computer in 2.5 years with probability 73%. And usually these are the kind of people that are also trying to sell you their post-quantum technology or are trying to get grants from the government. So I try to be honest and stick to the facts. And well, since some people are doing it, I think it works. So the idea of quantum computer, it dates back to Richard Feynman, which is one of the most famous physicists from the 20th century. And in year around 81, he had these ideas of a quantum computer not for breaking crypto, not for building company, but for simulating quantum physics, for simulating the behavior of subatomic particles and fundamentally understanding how they work at this level. So he asked the question initially if you could simulate quantum systems, or systems of particles that behave according to the laws of quantum mechanics, if you can simulate this behavior using a classical computer. So classical computer is any computer that behaves like a Turing machine or some equivalent system. So in particular, our computers, they work, they are classical computers. They have bits, they have a state, and they transform the state, and they give an output at the end. So essentially, you don't need to read everything, but the answer is here. It's no. You cannot simulate a quantum system using a classical computer. More precisely, you cannot simulate it practically. You can, write down the equations and try to solve the equations, but these equations, they will be way too big and it will take way too much time to solve. So we said that it's not practically doable because it would take millions of years. Whereas with a quantum computer, what he defines as a quantum computer, you could get this result efficiently. So if you know a bit about complexity and theory, in computer science, we usually associate hard to exponential or super polynomial, and we usually say that what is polynomial time or linear time is efficient, as a rule of thumb. Okay. So his idea was to have quantum computers that would simulate quantum systems, and it's not a Turing machine, but a machine of a different kind. So it's a different kind, it's not something that is much faster. I remember I had, at my place where I used to live, I had a washing machine, and it was written quantum on it. Maybe there wasn't any quantum behavior, but what the washing machine vendor meant is that it was much faster than the other one. Well, it wasn't really faster, but maybe it was a good marketing argument. Well, anyway, many people, when they read quantum, they think about science fiction stuff and think it's really fast, exponentially fast. But no, it's not a matter of speed, of latency. It's just a different kind of machine. So this different kind of machine, as you probably know, it does not work with bits, which are either 0 or 1. It works with quantum bits, which can be 0 and 1 at the same time, so to speak. So I have to simplify, but 0 and 1 at the same time means that you have a particle somewhere, maybe in a box, and you don't know its value. It's not 0, it's not 1, it's in a state called superposition. And this superposition state means that you do not know the value of the bit, and the bit doesn't have any value until you observe it, until you open the box. And this box is characterized with certain probabilities, but not exactly the kind of probability that we know. So the probabilities that we know, it's a number between 0 and 1, for example, 1/2, 1/3, in such a way that if you sum all the probabilities of all the possible states or events, it's equal to 1. So in the context of quantum systems, we don't talk of real probabilities, but things called amplitudes. So if you have a quantum bit that can be either 0 or 1, it's characterized by two amplitudes, alpha and beta. And these are not just between 0 and 1, these are numbers that can be complex numbers, so of the form a plus bi, where I is the imaginary number, and they can also be negative. But when you take the square of the modulus of this number, you end up with something that is like the probabilities that we know. So from the quantum probabilities, we can deduce the actual probability of observing 0 or 1. Okay. So a quantum computer is essentially a generalization of this. Instead of having one single bit, you have many bits. So if you have 8 quantum bits, you say, I have a quantum byte. If you have 1024 quantum bytes, you can say, I have a quantum kilobyte, and so on and so forth. But the circuit is not exactly the kind of circuit that we know, with XOR gates, NAND gates, and so on. It's a transformation of this state using relatively basic information. And in theory, what you just do is transform these probabilities, alpha and beta, and all the probabilities that you have, using basic linear algebra transformations. So if you remember in high school, you had this vector matrix operation, and you had certain matrices that can be invertible. So you multiply it by another matrix, and you can go back, get the initial result. So in theory, a quantum computation is just the evolution of a quantum state, where quantum state is just a bunch of quantum probabilities, and the new state is computed by applying this kind of matrix multiplication. And here, that's the reason why it cannot work on, you cannot simulate this on a classical computer. Because if you have 1 bit, you have 2 values. If you have 8 quantum bits, you have how many? 256, so 2 to the power of 8 possible values. So you have 256 probabilities to track. Now if you have 100 bits, you have 2 to the power 100 possible values. But you cannot store on your classical computer all these possible values, because there are just too many of them. So instead of storing 2 to the n probabilities, you just store n quantum bits, n quantum physical objects. And that's why you cannot simulate quantum computing efficiently in practice, because it would require exponential resources in terms of memory and in terms of storage. So to give you an estimate, we estimate that there's of the order of 2 to the power 80 atoms in the observable universe. So we can only store so much data in the universe. Okay, and at the end of the quantum computer, you observe one of these bits or a subset of these bits, and this is your result. Okay. So that's my best attempt to simplify a quantum computer. I don't know how clear it is, probably not very much, but yeah, I think that's the end of this part. Just to give you an idea that quantum computer is not much faster, it's not really faster, it's just different, and it cannot be simulated classically. So why I am here talking about this quantum thing is that there are some problems, specific type of computational problems, that you can solve efficiently with a quantum computer, and that you will never be able to solve efficiently on a classical computer. So it means that you can go from something that is practically impossible to something that is possible. And this phenomenon is called superpolynomial speedup. Well, quantum speedup in general is when you can do something faster on a quantum computer than you could do on a classical computer. Okay. So you have a list of problems. It's not any problems, it's only very specific types of problems. Maybe you know examples of problems for which we have this kind of quantum speedup. Factorization, of course, and that's the second reason why I'm here today. Maybe just one slide to maybe clarify this notion of quantum parallelism. I just told you that you can have bits that take multiple values at the same time. So it's tempting to imagine that, oh, a quantum computer is just a system that stores all the values simultaneously, and that will compute all the outputs at the same time, and that will just pick the best at the end. But actually it doesn't work that way. There's something called quantum parallelism, but it's not this naive notion where you can picture the computer computing all the results simultaneously at the same time and just picking the one that fits your criteria at the end. It's for this reason that you cannot break all cryptographic keys using a quantum computer. You cannot break symmetric keys efficiently, because it's still exponential. You cannot try all the keys, you cannot try all the passwords at the same time and just pick the best result at the end. It doesn't work that way. And another myth that, yes, sometimes people misunderstand, it will not solve all the hard problems. So maybe you're familiar with the concept of NP hardness, of NP complete problems. So all these constraint solving problems that you find, for example, in games, in scheduling problems, where you have to find the optimal arrangement of objects to have maybe the small size of or the smallest resource allocation. So a quantum computer would solve certain problems faster, but not these NP hard problems. So these are the problems where finding the solution is exponentially hard, but where verifying the solution is relatively easy. For example, if I ask you to find, let's say, a solution to some equation, maybe finding the solution of this equation is hard, but if you give me a solution, I can verify that it works by just computing the equation if the equation is not too complicated. If you have like a system of quadratic equations, x squared plus y squared plus z squared and this kind of stuff, so finding the solution is NP hard. It takes exponential time, or an exponential amount of resources, of energy, of whatever you need to do your work. But verifying the equation just consists in plugging the numbers, the solution in the variables and computing the equations. So these are the problems that, as far as we know today, cannot be solved efficiently by a quantum computer, nor of course by a classical computer. So last one, there's this notion of quantum supremacy. So it sounds like a Hollywood movie name. Supremacy sounds a bit impressive, but it doesn't really mean that everything will be quantum in a world. It will just mean that at some point we will have achieved a stage in quantum engineering where we have maybe a small, relatively small quantum computer, but that will be able to do something more efficiently than a classical computer. So it doesn't mean quantum supremacy, doesn't mean that all the crypto will be broken. It doesn't mean that everything will be faster, everything will be quantum, just that scientifically we have an evidence that it works. And we're not there yet, but not extremely far. So if you want to know more about this, I hope it's not too boring. If you find it interesting, this is maybe the best book I found by Scott Aronson, which is a very well-known researcher and blogger. Okay, so now let's go back to crypto. Maybe the single reason of why I'm here as a cryptographer. So you know the public key crypto systems like RSA, Diffie-Hellman, elliptic curve. You know, you use it for digital signatures, for key agreement, for encryption sometimes. But these all the public key crypto that we use in TLS, SSH, IPsec, it just boils down to these two problems. So it's secure because these two equations are hard to solve. So if I give you a number n, and I created the number n by picking two numbers, two prime numbers, p and q. So you don't know p and q, you just know n. And it will be extremely hard for you. It will be exponentially hard for you to recover the two prime factors. So as you probably know, in RSA signatures, the public key is n and the private key is p, n, or q. So if you know p and q, you can compute n by doing a multiplication. But if you know n, factoring n into p and q is extremely hard. And if it weren't hard, all RSA instances would be broken, which would be a bad news. And the other class of cryptographic problems is slightly more complicated equations. Instead of having three variables, we have four, y, x, d, and p. So here, you know y, you know x, you know p, and your goal is to find d. So let you look at it's very simple. It's x to the power of d, modulo the number p, which is a prime number, and you know y, x, p, and you know d. Sounds easy, but it's not. And of course, it's not because that's the equation that must be hard for the Diffie-Hellman problem to be secure. And for all the elliptic curve crypto that we use, so ECDSA in Bitcoin, in TLS 1.3, it's based on this equation. So these are hard to solve for classical computers, for normal people, even for non-normal people, but it would be relatively easy for quantum computers in the sense that the theoretical complexity would be polynomial instead of exponential. So exponential means hard, abelian means polynomial means easy. Okay. Now the good news is that we're very far from this kind of crypto apocalypse, which is how some people call it. The number of qubits we have in the best quantum computers today, designed by companies from Google or acquired by Google, Intel and IBM also working on it. So maybe IBM and Google are the leaders in quantum engineering today. So these computers, they have of the orders between 10 and 100 qubits today, depending on how you count physical qubits versus logical qubits. Yeah, around 50 or 70 anyway, it's not really many. But the numbers of bits we have in an RSA key is of the order of 1,000, so of the order of 200, 500 for elliptic curves. However, the number of quantum bits we need As far as we know today, to break this crypto is not hundreds, not thousands, it's millions. So why do we need millions of qubits when the key is so small, relatively small? Well, the reason is that a quantum computer is a very fragile system, very sensitive to perturbations from the environment, to the noise and everything, the temperature. So you need to correct errors that happen inside the system. And to do all these error correction, you need many, many other qubits. Because all these qubits, they might in turn have some errors, some perturbation from the environment. So you need to correct the errors in the errors and so on. So that's why you need so many qubits, and we're very far from this. And going from where we are today to such a big scalable computer is really hard, and we don't really know how to do it. So many people are working on it. Some people are very optimistic. Some people are less optimistic and will tell you it's never going to happen. But we can't really predict the future. It's of course really hard. And that's a research paper that tells you to break an RSA key, you will need this amount of quantum bits, around a few millions. And in terms of speed, it will not be instantaneous. It's not be, oh, let's click and then I get the result. They estimate in this case it would take less than 5 months. Okay, it's better than 5 millions of years, but it's not like you can break all the keys on internet in just 1 hour. So that's just an estimate of a few years ago, but it just gives you an idea of how slow or how fast it can be. Now maybe you know AES. So AES is the encryption algorithm we use pretty much everywhere in all the computers. It's the US standards advanced encryption system. Yeah, it's standardized by all the standardization bodies you can imagine. So it's the most common cipher. It's in all the Intel, ARM, AMD chips. You have the silicon implementation of it. So here it's not really broken. It's just slightly less secure. The security level is just a bit lower. So if you have a key of 128 bits, so instead of having a security of 128 bits, meaning that it will take you of the order of 2 to the 128 operations, it will only take you, in theory, of the order of 2 to the 64. So you just divide the exponent by 2. You square root the number of operations. So that's why people tell you, okay, to have the same level of security against a quantum computer, you just need to double the key size. So if you have a key of 256 bits, then you will get, in theory, 128 bits of security in the quantum setting. So again, it's really an oversimplification because in practice it's much more complicated. It could be much slower than this. And to give you a quick estimate, some researchers that try to estimate the size of the quantum computer that would break AES, because you have to implement AES, you have to implement whatever you want to break as a quantum circuit. And the size of the circuit would be of the order of 2 to the 80 or 2 to the 81 gates in terms of circuit depth. So if you estimate that each gate is the size of an atom of hydrogen, which is 12 picometers, this could be just only the size of the solar system, which fits in the observable universe, but which is still a pretty big computer. Now there will probably be improvements. It might be as small as maybe the moon or a big mountain, but it's still a relatively big computer. It's in the circuit depth. It's not the weight, of course. The weight is just 5 grams of hydrogen. But you see, it's not as simple as some people tell you. Okay, but again, you just need to double the key size, and the problem, and you can forget about this risk. Someone take pictures. Okay, do selfie. Okay, so now the title of this talk, if I remember correctly, was post-quantum something. So I only talked about quantum computing and not about post-quantum crypto. So post-quantum crypto is, as you can guess, about creating encryption algorithms or any public key system that would be resilient to quantum algorithms. So you can see it as an insurance. It's also called quantum safe, quantum resilient. And of course, if you want to be quantum safe or post-quantum or quantum resilient, you should not use factoring or discrete logarithm because these problems are broken, like I mentioned before. And it's not like, you can just make up a new problem in your office and say, oh, it looks pretty hard, I have no idea how to break it. It's probably post-quantum. No, it must rely on some problems that have also been studied for years and known to be hard for quantum computers. So for example, NP hard problems. This class of exponentially hard problems can, for example, be used for doing post-quantum crypto. Because what already happened is some people, they came up with a new construction that looked pretty exciting, but then people broke it, not in terms of, quantum computer, but they managed to break it just by using a classical computer. So of course, a quantum computer can do anything that a classical computer do, because it's a superset of a classical computer. Okay, so why do we care? I told you that maybe we're never going to see in our lifetimes any quantum computer. Do we really need to worry about it? So the way I explain it to people interested, especially customers, people who have to manage a budget, manage their risks, it's like an insurance. From your perspective, you see what information you have to protect, your assets, and from your perspective, what would be the risk of a quantum computer in 10 years, in 20 years, in 50 years from now? And do you have secrets or assets as valuable that you don't really want to take the risk to see them decrypted in 50 years from now? So if you want to eliminate this risk, which may not be a rational decision because there are many other risks in IT than crypto. Crypto is often the most secure component in a system. When it fails badly, but maybe you've seen in your job, there's many other issues, just, insecure software, insecure OS, you have security issues in Linux and Windows everywhere. So it's probably a bigger concern, and I don't even mention people and processes and all the real stuff. But anyway, NSA, that you probably heard of, National Security Agency in the US, in 2015 they published a memo where they said, "Oh, we anticipate a need to shift to quantum-resistant cryptography in the near future." So some people, started, crafting conspiracy theories and say, "Oh, maybe NSA, they have a quantum computer in their basement. Maybe they know things that we don't know, and maybe they're trying to manipulate us." You never really know. But from my perspective, NSA is just like the rest of us. They have to manage risk, and they have to manage risk not for a company, but for the United States, for the federal government. And if you've already worked in the public sector, you may know how long it can take to make changes in the IT of a government agency. So changing the crypto in all the federal agencies in the US, it might take 20 years or even more. So from my perspective, I think they're just being rational and prudent and just trying to buy an insurance. And I don't think they know much more than we know. Maybe they know a little bit more, but NSA is not renowned to have teams of physicists and quantum engineers. So the NIST agency, which is the agency in the federal government in the US responsible of the technological standard, they started a project called Post-Quantum Crypto Project. It started 2016, 2017, depending how you count. And the goal, the end game, is to standardize new public key crypto systems that would be quantum safe, that would be post-quantum. So it's completely public project. You can go to the website, there's a list of submissions. And the way it works is like they did for AES, like they did for the SHA-3 hash function standard, is that they put out an RFP, a call for proposal, and then many researchers they work very hard. They have budgets of millions of euros, dollars, whatever currency. And most of the time, these researchers, they are from Europe. They have some researchers from the US, but many submissions from Europe. So they essentially work for free from the US. They give out all the IP, all the copyright, and then the NIST agency picks the best. So I think it's a win-win game because for researchers, they get taxpayer money as research grants. They get interesting topics to work on. They get publications. And the NIST agency, they get what they need for a very small budget. Because if you're in a company and if you want to build a new crypto algorithm, it can cost you, several millions, or more money than it would cost you to organize this, of course. So if you look at the website, if you're not a cryptographer, it will be pretty confusing, and you'll see many words that you don't understand, and so many words that as a cryptographer I don't understand, like lattice, base, ring, LWE, SVP, vectors, and this kind of stuff. So to summarize, there are essentially four and a half, five families of post-quantum systems. So lattice base, code base, multivariate, hash base, and other like isogenies. So the first family, lattice base, I don't know if you're familiar with this, maybe not because it's not used a lot yet. It's not something, very esoteric, and it's not really new. It's something that's been studied for many years. And Google actually experimented with it a few years ago when in Chromium, so the development version of the Chrome browser, they integrated a hybrid key agreement scheme that was based on something called New Hope. So New Hope is just named like this because the designers, they're huge fans of Star Wars. And they just tested it in Chrome and then they removed it. Not because it was bad, but because that was the plan from the get-go, just to test it and do some performance measurements and then think about it. So what Bruce Nair says, so Bruce Nair is a very well-known security expert. So he said, secure public key algorithms are very hard to create, and this one, so he was talking about New Hope, hasn't had nearly enough analysis to be trusted. Lattice-based public key crypto systems, such as New Hope, are particularly subtle, and we cryptographers are still learning a lot about how they can be broken. So I think that was a reasonable statement. And the goal of the project I mentioned before, which spans maybe 4 or 5 years, is to have many people trying to break these systems in order for us to get more confidence and understand what makes a post-quantum system secure and how, also in terms of performance, how to implement it efficiently and securely. So 2 other families, interestingly, they are based on very, very old techniques. In the late 70s, I wasn't even born, people such as Michaelis Niederreiters, they studied error correcting codes, and they managed to build a public key crypto system based on error correcting codes. And interestingly, when you look at the submissions in the NIST project today, one is almost identical to the one published by Michaelis in the 70s. Another type of post-quantum systems is similar to what I mentioned before, when I was talking about quadratic equations and a system of equations that you have to solve. So this is the family, what we call multivariate polynomials. So multivariate, as opposed to univariate, is when you have multiple different variables, so x, y, z, b, and when you have equations that are not only additions, but also multiplications. For example, x times y square plus z times b square plus 5 equals 3, and this kind of stuff. So you have approximately as many equations as variables, and your goal is to find one solution to the system. So again, these are 2 systems that, in theory, are NP complete, are NP hard problems, which means that they should be hard. But there's a small catch, because we want these systems to be not only secure, but to be efficient. We want the key to be maybe less than 1 gigabyte, because a key of 1 gigabyte would not be extremely convenient in a X509 certificate. So we have to find maybe workarounds to simplify these problems to make them relatively small. But the smaller you make them, the smaller you make the equations, then the less secure it tends to be. So the job of cryptographers is to maximize the security and minimize the resource consumption, so maximize the performance. So the last part of this talk, and maybe the more technical, so if you're afraid of technical stuff, well, I'm sorry, but it's relatively simple. It's maybe the simplest of the 5 families that I've mentioned. So funnily, these are only based on hash functions. So hash function is like the most stupid cryptographic algorithm you can imagine. And that's why I did my PhD on it, because it's so simple. A hash function, it just takes whatever piece of data, 1 bit, 1 megabyte, and it transforms it into a small fingerprint, a value of maybe 256 or 512 bits. So it's also called a one-way function, or hash function or one-way function. And sometimes cryptographers make it, complicated and esoteric, but it's relatively simple to create a hash function. It's much harder to analyze, but we have pretty good hash functions like SHA-2 and SHA-3 and Blake-2. So I think it could be a good building block to create public key crypto. So we take something that has nothing to do with public key crypto, hash functions, and we build digital signatures. So a digital signature, as you know, you have public and private key. You use the private key to sign. So private key is like your knowledge of how to create the signature, and the verification is just you need the public key to verify someone's signature, and of course you don't know their private key. So they're really unique compared to all the others in the sense that they don't use any mathematical concept, no idea of equations, of mathematical structure. It's not about NP hardness. It's very straightforward. And you have this notion of reduction. So reduction means that you can relate the security of two systems. And here we have security proofs that tell you that as long as the hash function is secure in terms of collision resistance, in terms of pre-image resistance, then the signature scheme will be secure as well. So in other words, if you want to break the signature scheme, you need to break the hash functions. And good luck breaking SHA-2 or SHA-3 or Blake2. And yeah, we have hash functions. The only problem is that it makes big signatures and it's slow. It's super slow. Well, it depends. To generate the key, in the system we created, it took of the order of 1 or 2 seconds. To sign a message, it took of the order of milliseconds. And to verify it, it took of the order of microseconds on a typical laptop. But signatures, they can be pretty large. If you look at ECDSA, RSA signatures, maybe at most 1 kilobyte. In our case, it would be between 20 and 40 kilobytes, so much bigger. And sometimes you have this problem of statefulness, meaning like you have to store a counter to count how many signatures you've done before. But it's not, it's not needed for any system. So let me present you the most stupid cryptographic construction of the whole humanity. It's so stupid that it's hard to understand why it works. So the key pair is 2 strings, K0 and K1. Okay, big enough. So these are your private key, K0 and K1. You know, the first one and the second one. And you take your hash function and you hash K0 and you hash K1. And these will be your public key components, 2 hash values. And that's it. So it's instantaneous to generate public key and private key. Now if you want to sign, there's a small limitation, a practical limitation. You can only sign a message of 1 bit, which is 0 or 1. And you can only do it once, so better get it right. So if you want to sign the bit 0, you just publish K0. Say, okay, K0 is my signature. And if your message is 1, K1 will be the signature. I want to give you 10 seconds to think about it because it doesn't make any sense. You publish your private key, you don't do anything, you don't sign, you don't make any computation. But the idea is that if you know the public key, you know the hash of K0 and the hash of K1, what you want to make sure is that the message you receive has been sent by the person or the computer that knows the private key, by the person that knows K0 and K1. So if you reveal K0, if you show that you know K0, then you prove to this person that you're the one that knows the image, the pre-image of this public key component. So you're just proving that you are the same person than the one who gave them the public key, and that's the concept of public key signature. So if you want to make it more useful, because that's completely useless as it is, well, you need as many keys as there are bits, and you can use a key only once, so it's completely stupid. But you can sign more than zeros and ones. You can sign 0, 1, 2, 3, 4, maybe 5 or 6 or 10. So instead of hashing the key once, you hash it many times, and then to verify the signature, you hash, you do a sequence of hashes. So I'll give you the slides and you can figure out how it works. But then we still have the problem that a key must be used only once, and that's unfortunate. So in computer science, in many cases, you're stuck with the problem, and what do? You use trees. I mean, Bitcoin is using tree, all many data structures are using trees. Trees are extremely convenient because you can get rid of exponential storage by having to store just the root of the tree. So in this case, if you want to have one small public key and many potential private keys, so you generate the keys K1, K2, K3, K4 in this example. You compute the hash tree by hashing these 2 together, and you get the root. So here, the size of a rectangle is not the size of the value. All the values here are of the same size, namely the size of a hash value. So you hash all your private keys, and then you get the root of the tree, which is another hash, and this would be your public key. So when you're going to sign a message, you're going to pick the first private key, K1, and you're going to use it only once. And what you want to prove to the verifier, so the verifier only knows the root, you want to prove them that your key is connected to the root. So to show the connection, you will give them, if you sign something using K1, then you will give them this value, which will allow them to hash these 2 guys together, and you also give them this value, which will allow them to hash these 2 and to recompute the root. In other words, you give the verifier the hash values that are necessary to go from the leaf to the root, which will show them that the key that you use is kind of part of the public key. that you publish beforehand. And then if you want to use another key, you're going to give the other intermediate values. Okay. So these are relatively simple, but if you look at the candidate standards in the NIST project, there are some extremely complex constructions called Sphinx, Sphinx Plus and Gravity Sphinx. And they use not only this kind of tree, but they use hypertrees. So hypertrees, it's trees of trees, right? Each node is another tree. Doesn't seem to make a lot of sense. It took me maybe a few weeks to understand how it worked. But the idea of this is to have at the end, at the very bottom of the tree, so you have this tree of trees and so on. And at the very bottom, you have a bunch of leaves. And is to have like a virtual tree where you will have maybe 2 to the 60 leaves in the tree. And instead of maintaining a counter 1, 2, 3, 4 of each key used, you will pick a random index. You will pick a random number, and this will be the index of your private key. And then your goal will be to, as a signer, to give a proof of a connection between the key that you use and the root of the tree. But I'm going too technical, so I'm going to conclude. I have 1 minute left. That's perfect. So if when a quantum computer is built, then this will be good news for many people, but bad news for many others. All the public keys could be broken, all the public keys we use today, all the TLS certificates. So if you have TLS certificate, there's a public key inside, and if you can break the public key, you can retrieve the private key and hijack all the sessions and man in the middle of all the sessions. You don't really have to worry about the symmetric key security. Well, maybe I shouldn't say this because in theory, some people would not agree with me. In theory, yeah, it will be at most half, but in practice, it will not really be like this. So post-quantum crypto, it's again something that would not be broken by quantum computers. Would we have any quantum computers in the future? So NIST is working on this competition. It's really exciting. If you're interested in learning more about this, just Google it, because all the code, all the specifications are public, and they expect the standards to be released around 2021, 22, 23. Maybe they will announce the standard in 21, 22, and the draft will be published 2 or 3 years later, like it happened for SHA-3. And, well, nobody's sleeping. That's good news. Well, thank you very much for your attention. I will be around for questions.